final review, and that's because our final exams start tomorrow. So that means that you guys will need to take your final exam sometime between midnight tomorrow, is like midnight in a couple hours, and 11:59 on Thursday. Okay, if you have anything that you want to turn in today, like test corrections or ELOs or anything like that, that must be turned in by 11:59 p.m. tonight. Now, last week I tried to share this some more, oh dear, link with y'all. Like I did a screen share, and that did not work. It looked like on the recording you could only see like half of it. So is I am going to, and I apologize in advance for my cough. I've had this cough for a while now, but there's apparently nothing they can do about it. So I'm just gonna share some important details and all. So you must take it sometime between Wednesday and Thursday. Um, it doesn't matter when you take it. You could take it at, 12:01 this morning, or tomorrow morning if you want. That's totally acceptable. But you need to have 90 minutes in a row to do it. Okay, so it's 90 minutes, and it must be done all in one sitting. So you can't come back to it. In addition to that, um, it's worth 20% of your final grade. So that's like equivalent to like every lab we've done this semester. So it's a big portion of your grade. So please take it seriously. We can't exempt the final, and it basically covers every module but the excuse me, the math of physics module. It has 45 questions. And if you go to this link, it breaks it. So if you go to this link, you can see the breakdown for each question, like how many are in each module. In case you want to study, you might want to spend more time on the modules that have more questions and less time on the modules that have fewer questions. Test corrections are a great way to prepare for this, and also those synchronous session ELOs. Not only will they improve your grade in the course, but they will also help you study for the exam. So, and then if you want credit for any of those, you have to turn them in or 11:59 tonight. So please don't email me tomorrow and say, oh, can I turn in my test corrections? Because I can't allow it. It's virtual school policies. It's not even my personal policy. So, yeah. So let's get into the good stuff. Basically, what I did is I went and I found the question. I went and looked at all the tests and found the questions that students the most, and those are the ones I'm going to go over. There's a bunch because there's like 3.5 units or whatever. So I'm going to try and go fairly quickly. So let's see. So these are the formulas that you should have on your formula sheet. If you don't already have a formula sheet, you should go ahead and make one. And from all the reviews, I've got, formulas for all the units on there. If you do have a formula sheet, just kind of double check it with what I've got and make sure that you've got all the formulas you need for your final exam. So here is one of the first questions that was frequently missed. And I'm going to try and, like I said, I'm going to go through them as quickly as I can just to try and get through as many as possible. Again, I'm so sorry about the cold. So this one says, what is the wavelength? So that's going to be lambda of a wave with a velocity of 5.28 meters per second and a frequency of 7.39 hertz. Okay, so we have lambda is what we're looking for. Our frequency is 7.39 0.39 hertz, and our velocity is 5.28 meters per second. Our formula is lambda equals v over f. You could put it in a triangle, but since we're looking for lambda, we don't have to do that. So we can just go ahead and plop our numbers in and get an answer. Okay, so this one isn't too bad, but like I said, it was missed kind of frequently, so I wanted to go ahead and go over it. Go to another one. So basically in this one, we've got these two pulses are heading towards each other. And so we pick a color that you could see. So they're heading towards each other. So when they meet, since they're both like, let's say this was our rest position. Since they're both above the rest position, we will add them together. So this one is basically like 2.5 squares ish, and this one is like half a square. So what we would do is we would just add those together. And we would get like 3 squared. And then in the actual key, I believe it has a picture. And so, you pick one that had something like that where it was like 3 squares tall. So that's going to be your resulting displacement for these guys. So for this one, it wants to know which harmonic is represented by the standing wave. And so what we can do is we can just kind of like count the number of antinodes. So like this would be 1, 2, 3, 4. So then this would be our fourth harmonic. And that's all you have to do for that question. Next, trying to get to the one that take a little more effort. Okay, so how much power is necessary to produce a sound wave with an intensity of 3.16 watts per meter when the wavefront is vibrating with an area of 1.69 meters squared? So power is in watts, and that's what we want. Our intensity is 3.16 watts per meter squared, and our area is 1.69 meters squared. For this one, we're going to use this formula, and we're going to have to put it in the triangle because we're looking for power. I mean, you could do algebra, but I'm lazy and I don't like doing algebra, so I just throw things in the triangle. I'm looking for power, so I'm going to do intensity times area. So that's going to be 3.16 times 1.69, and that would be 5.34 watts. So this one is a Doppler effect question. So it wants to know the Doppler frequency. So that's going to be that F prime in that formula. And we'll have a 211 hertz sound wave, like F regular, and it's moving away from a stationary observer. Okay, so this means that's the velocity of our observer is stationary, which is 0. And its source is moving away at 45 meters per second. Okay, so that's going to be Vs. And then we're going to use 345 as the speed of sound. Okay, so we know F is 211 hertz. We know the observer is 0. We know our source is 35 meters per second. And I'm just going to put in parentheses away because it's moving away, just so I remember. And then 345 meters per second. And then I'm going to take my formula. And now remember, for this formula, there's a rule as to like what is positive and what is negative. I'm going to get that for you right now just so you can have it. If your observer, if your VO is towards the source, then you're going to have a positive. And if your VO is going away, so I'll do that for like away, then it's going to be negative up here, this sign right here. And then if your VS is going towards the observer, you're going to be positive. And if your VS, I'm going to do this for away, is going away from the observer, it's going to be negative. So since we're going away, we're going to do a negative right here. Okay, so now I'm just going to plug in my numbers. Okay, so remember, this was a negative in the formula, and then since we're going away, this is another negative. So it'll actually end up adding. So then we've got over 390, and then we'll end up with 186.7 hertz. So now we have the electromagnetic radiation optics unit. Again, these are formulas that if you have a formula sheet, cross-check these formulas with your formula sheet to make sure you've got these on your formula sheet. If you don't already have a formula sheet, go to these reviews and at least look at these formula pages and write all these down so you've got them all, because there are way too many formulas in this course to try and memorize them all. That would be ridiculous. So make sure that you've got that formula sheet. You've got it all written down, all the formulas. Okay, so this one, it's kind of like a waves question because we're using that same like frequency velocity formula. The only difference is because it's an electromagnetic wave, they don't give us the velocity because they expect us to know that. So our wavelength is 6.43 times 10 to the 2 meters. And then our velocity is just the speed of light we have memorized to show up. If you don't, maybe do that. 3 times 10 to the 8th and 9.8 meters per second squared are the two numbers that I think all physics kids should memorize because we use them fairly frequently. For this one, in a triangle, so my frequency is going to be my velocity divided by my wavelength. My velocity is 3 times 10 to the 8th, and my length is 6.43 times 10 to the 2. And so that's going to give me 4.67 times 10 to the 5 meters. Sorry. I just looked at it, I was like, why did I write meters hertz? For frequency. Sorry, that's hertz. I try and work these out ahead of time just to make sure I don't make too big of a mistake while I'm trying to speed through them. So, next one. Okay. So this one is a frequency one, but it's giving us energy that of a wavelength or something like that. So we'll have to use a different formula. Our frequency is hertz. Our energy is 3.18 times 10 to the negative 21 joules. And our formula is this one right here. And so this H, I would write this H on um, I don't, that's not one of the numbers that I usually expect kids to memorize. So I would write H on your formula sheet. Um, that way you've got it in case they don't give it to you. For this one, again, you're going to have to um, put it in the triangle. Looking for frequency again. So we've got 3.18 times 10 to negative 21 over 6.626 times 10 to negative 34. And then we have, that is 4.8 times 10 to the 12. So there's our frequency for this one. And like I said, just make sure you put this guy on your formula sheet in case they don't give it to you on the test. Okay. The image distance for a real image is just positive. Okay, so it doesn't matter what type of lens or anything you're working with. If you have a real image, the distance is going to be positive. The object distance is also always positive. Um, so those two were missed quite a bit, actually. Now this one wants you to finish the ray diagram. Okay, so it would give you multiple choice options that look like this. So basically with this one, you could see they're like going through the focal point at the top of the image to the mirror, and then it's going to go horizontal right here away. Okay, so you would pick the choice on the like multiple choice or whatever that look like this. Okay, so it's going to go angled and then horizontal, which every time we work through these lens or mirror questions, they're going to have an angled portion and then a horizontal portion. So to fill in that horizontal part. Okay, so now we've got a curved mirror math question. And I think what a lot of people did on these is they just didn't know their sign connotations, for example, like on this type of mirror, there's if your image is behind the mirror, then it's going to be a negative image distance, or if your object is your image is upside down, you'd have a negative height. So I think that's really, from what I could tell, on the short answer part was really where people made their mistakes. So we have a 10 centimeter tall object and we're placing it 8 centimeters in front of the mirror. That's our object distance. This is telling us that we use mirrors instead of lenses, and it produces an image that is 6 centimeters behind the image or behind the mirror, and then we want the focal length. Okay, so let's see what they gave us, because I get the feeling that they probably gave us something that we didn't need, and sometimes that throws folks off as well. And this is going to be a negative, and it was the focal length. Okay, so we're going to use this formula. Okay, so they gave us this height. We don't need that. They could sorry again for all the coughing. Um, they could always give us another problem. What they did is this is probably like a standard problem, and then in another one they might ask, you know, what was the image height or something like that. Um, but in this one, they want the focal length, so we don't need that. So I'm going to do 1 over f is equal to 1 over -6 plus 1 over 8. And then what I like to do is I like to immediately convert these to decimals because I don't like working with fractions. I've seen a lot of people too, they stop here. And they're like, okay, I'm done. Well, that's 1 over f, right? So to actually get f, um, you have to do 1 divided by that. So if you get like a really, really small number for your focal length, that usually means that you probably forgot that last step. So there's our focal length. Okay. Now, this one is a magnification question. So we have an object that is 10 centimeters tall, and it's 8 centimeters in front of the mirror. So we have that's our DO, and our image is 4 centimeters in front of the mirror. We want the magnification. Okay, so again, we are probably not going to need all of these numbers, but I'm going to go ahead and write them anyway. And then I can just pick and choose what I want. And we want the magnification. Okay, so our magnification formula is okay, and we only need, right, one of the two of these. So since we already know DI and DO, we don't have to, you know, bother with this. We can just do -4 over 8 and get -0.5. So that means our image is likely going to be upside down, and it'll be half the size of the object. So, you know, if they ask you, like, you know, then they ask you what it would be 5 centimeters tall instead of 10. Onward. Okay, so in this one, this is just like a concept question, and it basically is just telling us, you know, when we're measuring our refracted ray, how are we going to measure it? And we're always going to measure it from the normal. Okay. Um, your answer is definitely not going to be if you see something with like usually like that. Those are definitely not a choice, you know, because then how would you know, right? How would you know how you were going to measure it? And so when you see something like that, you can cross those out, and then it's really, is it measured from the normal or the surface? And it's the normal. And remember, the normal is this perpendicular line right here. So onward. Okay, so here is another ray diagram one, and this will give you images of a ray diagram for your choices. And then, so for this one, this is the one that goes straight center. So it's just going to keep going through the center, except obviously be straight and not wiggly like mine. Onward. What is the angle of refraction of a ray that makes an angle of 35 degrees? I try to pick also questions. If there are multiple ones that were missed, I try to pick ones that give us a little. We could practice different formulas. So we want the angle of refraction. Okay, so that's refraction is theta 2. If that ray makes an angle of 35 degrees, theta 1 with a normal in quarts. So that's going to be our N1. I shouldn't have made that I. And then travels to water. So it's N1 to N2. So for this, we're going to use Snell's law. And biggest thing I've noticed, not necessarily in this particular class, but in general in my time teaching physics, is that students tend to get what is N1 and what is N2 mixed up, and then they get the wrong answer. So just make sure that you've got those correct. And that's why I like to write them here, because then I don't accidentally like pull quarts and put it in for N2 and then, accidentally put water in N1, even though I do know, the right one. I just didn't, put it in there correctly or whatever, because I just pulled the wrong one from the formula or from the question. So I'm going to have 1.33 and sine 35. And if I wanted to put this in the calculator all at once, I would put in extra parentheses here, just to make sure that my calculator doesn't do something wonky. Sorry. See what I did? I'm looking for theta 2, and I just totally solved for theta 1, which is exactly what I was saying that students do when they make mistakes. So it's not just students, it's teachers as well. There we go. Okay. Oh, where you belong. And then, so then I would get, I would have sine of theta 2 equals 0.670. That is not my answer, right? That's not our angle. What we need to do then is I'm going to move my problem over here because I ran out of space. So then I'm going to have 2 is equal to sine, inverse sine of that number. Okay. And then I'll get a degree. So same kind of thing. If you get a number that's really, really small for your theta, you probably did something wrong, and you need to make sure you take the inverse sine before you, decide you're done with the problem. So, Ken, I'm really sorry about all the coughing. I went to the doctor today, and they're like, "Yeah, I can't really do anything about that." So, okay, so this one is a critical angle formula. So we're gonna look for theta c, and we have a ray of light in crown glass. So that's N1, and it's headed into water. So since it's headed into water, water will be our N2. So we're looking for theta C. And we have N1 is crown glass, N2 is water. And our formula for critical angle is this. So then we'll have to do 1.33 over 1.53 we're going to get this tiny number. And remember, that's not our answer, right? We have to take the inverse sine of this small number. And then I'm going to write it up here just so it's easier to see. Didn't work out exactly the way I planned. And we're going to get 60.3, which seems a lot more reasonable for an angle than 0.869, right? So that is that one. Okay, now we have a lens one. So let's see what we've got. We have an object that is 5 centimeters tall and is placed 3 centimeters from the lens. It produces an image that is 4.25 centimeters behind the lens. So that's our DI. And then we want the magnification. Okay, so let's see what we've got HO is 5 centimeters. This is another one of those where they gave us more things than we need. What I like about magnification is it has no units. So I don't have to worry about forgetting units. Okay, so since we have DI and DO, I'm not going to use this HO part. And I'm just going to do my magnification is equal to these guys. So I'm going to do negative 4 point divided. There we go. And that's going to be negative 1.42. So it'll be upside down, and it'll be like 1.5 times, basically, the size of the object. Onward. Okay, so this is a diffraction question, and it's thin opening. What's going to happen? And basically, it's going to diffract, right? That's what happens with our thin opening. Is it and basically, kind of the definition of diffraction is that the wave will act as a new wave source. So that's going to be our choice right there. Is choice D, and that's basically because that's kind of the definition. Onward. So this one uses a formula that honestly we did not use in our. Okay, so we need the angle of the second order bright fringe produced by two slits that are this far apart, and if the this. Okay, so look for this. So MS2 or D is 8.25 times 10 to the negative 5 meters, and our wavelength is 4.5 times 10 to the negative 7 meters. So here's our formula. And we're looking for theta. So we'll have theta equals, which is 2 times 4.5 times 10 to the negative 7. Okay, and you see how I put the two parentheses there because we need we want to put it in the calculator all at once. Otherwise, your calculator may divide things instead of multiplying things and just make a mess. Okay, so this again is the sine of theta. So it's not actually theta. So to get theta, we need to do sine or inverse sine. I was going to say sine of -1. And this one, believe it or not, is going to give you a really small number. But at least it's not as small as this one, this 0.109. So this is going to be our angle onward. Okay. So those were the most frequently electromagnetic radiation ones. Now we have electricity. Again, make sure you've got these formulas on your formula sheet. If you don't, go ahead and put the ones that you don't have on there. Don't have a formula sheet at all. Then add these to the formula sheet that you're making. So what is static electricity? Static means not moving. Remember, static friction was not moving friction. So static electricity just means that the charges are not moving. They're all in one place. So what is the charge of 2.24 times 10 to the 13 proton? Okay, so this is our number of protons. So we're going to use this formula that looks like this. And then Q is the charge of a proton. And then big Q is the charge of all of those protons. And then N is just the number. Okay. So this kind of reminds me of a chemistry problem, like when you did when you do chemistry stuff, because you're like how many atoms or whatever, and you just kind of add them together or multiply it together. 1.602 times 10 to the -19 times 2.24 times 10 to the 13. And we'll get 3.59 times 10 to -6 onward. Okay. What is the magnitude and direction, excuse me, of a force applied to a 368, I just call it UC charge, so Q, placed in a 581.00 newtons per coulomb electric field, and it's pointed to the left, and our magnitude is our force. Okay, so the first thing we need to do is we need to take this and we need to turn this into coulomb, because we have to have coulombs in our formula. Pause my voice for a second. Okay, I'm back. I still want you to have to hear me hacking up a lung. Okay, so here's our formula, and then I'm just gonna put my numbers in here. And I'm going to get Okay, and then we need our direction, right? We can't just skip that. So basically, since we have a charge, it's going opposite the direction of the field. So since the field is pointed to the left, we're going to be going to the right. Uh-oh. Stay there. So that's that direction. Okay, so let's do some more. Um, okay, in this one we have a 4 coulomb charge moves across a potential difference of 7 volts. And then what is the change in electric potential energy? So that's delta PE. So we have Q is 4 coulombs. Our voltage is 7. And we want the change in potential energy. So we're going to use this formula. Um, like this. And then we're just going to do 4 and 7. And we're going to get 28. I think I could do that in my head. What must be the current? It's going to be I in the resistor if a in potential is 0.75 and uses 2 watts of power. Okay, so our volts are 0.75 and our power is 2 watts. And we need current. Our units for current are amps. I still think it's weird after all these years that current, the symbol in a formula is I, but then the units are amps. It's weird to me. So this is our formula, P equals I over V. Do I, V, P. We are looking for I. And so we're going to have 2 over 0.75. We're going to get 2.67 amps. Onward. Okay. So this one is a equivalent resistance in a parallel circuit. I see kids miss this all the parallel circuits. And I get it because you have to use a fraction, and I don't really like fractions either. But you have to do this. So then you get like 1 over 2, this 1 over, this 1 over 6, that's 1 over REQ. And like I said, I just whenever I have a fraction, I just like to go ahead and put stuff in decimals. I have to deal with fractions. Maybe I'm lazy. Okay, so then I get 0.917, and I see students stop here too. But you know, that's 1 over REQ. That's not actually REQ. So to get REQ, to do 1 divided by 0.917, and then you'll get you know, something a little more decent. And just to like a rule of thumb with a circuit, your equivalent resistance is less than any of these numbers up here. So if you get something that's more, you know, you probably did something wrong. And then with a series circuit, it's going to be more than any of these numbers. So that's kind of a way to kind of double check your math. Okay, so pull of a minute. So interesting about the Earth is that on the Earth, our this is our like geographical North Pole, and this is our geographical South Pole. Never. Magnetic north is this is actually magnetic south up here, and magnetic north is down here. And then every so often they'll actually swap. But right now we're in a part where magnetic south is at the top and magnetic north is at the south. And so the north pole of a magnet is going to be attracted to the north pole of the Earth because that's actually the magnetic south, which is kind of confusing, but they're just basically backwards right now. And then, in a few thousand, lots of thousands of years, it may switch back the other way. So magnetic fields, basically what goes on in a, if you want to draw these magnetic field lines, they, they go away from the north to the south. So they're going to point, they're going to pour to the south because they start at the north and go towards the south. Okay, so this is one of those right-hand rule questions. And I'll be honest, I struggle with the right-hand rule. I don't know if it's because I'm right. And so I always want to do it with my left hand because I don't want to put my pencil down. But basically, you want to take your and have it go in the direction of the arrow on your right hand. So I'm going to try and draw like if this was my right hand. I'm not really a very great artist. So, and this would be like my palm right here. So my fingernails would be like on the other side. And then your fingers can like kind of curl around the arrow, and that's going to tell you what's going on with the magnetic field. Okay, so basically you're going to kind of curl like this. So and it'll go like kind of in front of this line. So C is supposed to be in front of the wire. It'll be pointing, and then like A would be pointing upwards, and going up, and then B would be going down. So you've got this, this circle like this. It's going kind of in this direction, if that makes sense. So C would be down. Okay, so now let's do another magnetic question, and then this is our last kind of magnetic question that was missed, and then we'll go to nuclear physics, and then we'll be done because I know we're kind of on time. So here's our force. This is a 381 Coulomb charge. It's moving perpendicular to a magnetic field that is 1.26 Teslas, and our velocity is 8.27 meters per second. So we've got a Q of 3.81. We have a, sorry, I don't know why I put a B, I mean an F here. I meant to put a B. Still back on force, I guess. 1.26 Tesla, and then 8.27 meters per second. And then our formula is FQVB. So you could put this in the triangle if you wanted. Like if they asked you for something else, you can just divide the triangle into 3. But we're looking for force, so we don't need to do that. But just in case you need to do that on another problem. So we'll just multiply all 3 of these guys together, and we'll get 39.7 newtons. That's that one. Okay. Next. So nuclear physics, there aren't a ton of formulas. So I put these two, but then I also wanted to have like a kind of like a basic what an alpha formula would look like, and then what like a beta formula would look like, and then what fusion looks like, and then kind of like how to calculate half. Um, so that's what those are. Okay. So we have an element with an atomic 90 and an atomic mass of 230. Okay, so this is you know, if we were going to write it, it would look something like this. And then we, you know, that would be our element or whatever. So for alpha decay, I'm going to write kind of the key over here for the -4. And then for the atomic number, you'll -2. For beta decay, you'll do the mass. Mass doesn't change. But the atomic number actually gets bigger, so you'll add 1. And then for gamma, it doesn't change at all. So like the mass, you know, you can -0. And then, so this is telling us for alpha decay. So we're going to have to do 230 -4, which is 226. And then we'll have to do 90 -0, which will give us 88. You could look up, you know, whatever element that is. Onward. Okay. So the decay of a single radioactive atom. Now they're not saying the decay of like an element. They're talking single particular atom. So like if you had, you know, like a bucket of atoms, a whole bunch of atoms in here, like the likelihood that like this particular atom right here would be the one undergoing radioactive decay. That's what they're getting at in this question. And that's purely random. Which atom, you know, out of this sample is going to decay. We know, you know, statistically that, you know, a certain amount is going to decay each time, but we don't know, you know, that whether it's this atom or this atom that's going to be decaying like right now. So that's kind of what they're getting at there, the decay of a single atom, not necessarily the decay element. This one, it's asking for the decay rate. And so our sample has atoms in it, many atoms, and then we have a decay constant of this. And so we want the rate. Okay, so our rate is going to be delta N over delta T. Okay. And so our N is 3.18 times 10 to the 22. And our lambda is 0.283 per second. Okay, so we'll use this formula. Like I said, this right here is basically telling us that that's the rate. So it's not like that's, you know, two things that we need to solve for or whatever. So then we get 9 is 10 to the 21, and they call that BQ. Next, so I know in the module they tell you just to like take it and like divide by 2. I've always done it calculated half-life by using these arrows because it just helps me. I can just, when I'm done, I can just count the arrows. So like 1 half-life. And then also if I know like, one half-life is 10 years, then I could put like 10 years here and then, for the next one. But then it's basically the same thing, right? 9.1 times 10 to the 18. If I'm going to divide that by 2, I'm going to get 4.6 times 10 to the 18. Okay, and I want to do another half-life. I'm just 10 years because then, I could then go 10 years, whatever. And then there I'm going to get 2.3 times 10 to the 18. So then this is going to tell me how many atoms are remaining. This will tell me how many half-lives have passed, which is 2. And then I can take the 10 plus the 10 if I wanted. And that would tell me, how long, how much time has passed or whatever. So that's why I like to do it this way, even though it's not like a particular formula. It's just, I don't know, it works better in my brain. But you can keep doing it the way they ask you to, the math they show you in the course. Now for this one, they want you to determine the half-life of that isotope here, or that time. So basically, from here to here, that's a half-life, right? And so that's 0, and then this is about like 0.12. So that would be our half-life or our time. And you could do it from here too. That would give you the same amount. But it's just easier, from this first one to the second one, because in the first one we're starting at 0, so we don't have to like do math or anything like that. But you could do this one to this one, and you would get the exact same answer. It's just a little easier to do it in the first one. Okay, so fission. Fission is basically is used in a nuclear power plant. And so fission is going to produce energy by converting mass to energy. Okay, so this is, none of these are not necessarily true. We do use uranium in a nuclear power plant, but you can use other elements. It's just that uranium's easiest for us. But that's how I remember that, is fission is what we use in a nuclear power plant right now. And it basically uses energy. So does fusion, I guess, but they weren't asking about fusion. Okay, so this is a fission reaction, and we're just going to choose the right isotope to go in the blank. So for this one, they'd give you a bunch of choices. Basically, we need to do 239 plus 1, and then we're going to minus, whatever's on this side. So we're going to minus 103. And then this is a 1, but there's like 3 of these ones. So that would be like, 3. So we'll basically have like 240 minus 106. Which would give us 134. I'm going to do the same thing for the bottom. So I'm going to have 94 plus 0 minus 40, because that's from the other side, and then minus, 3 times 0 is 0, so minus 0. Just like 94 minus 40. So we'll get 54, and I'm going to put it here. So we'll have an element that's 134, and they'll give you a bunch of choices, and then, the choice that isn't correct for this one ends up being XE. But that's how you get that math anyway. And now let's try another one. This is a fusion reaction. So we're going to do the same thing. We're going to take 2 plus 3, and we're going to take 4 away from that. So that'll give us 1. And then I'm going to do 1 plus 1, these two bottom ones, minus 2. So that's going to give us 0. So then, they'll give you a bunch of choices, and this would be your correct choice, the 1 over the 0. Okay. And that's the last question I have for you guys.